What if the biggest mistake we've made was waiting for aliens to talk to us? For 60 years, we've listened, scanning the sky for a hello buried in static. But radio fades, civilizations collapse, signals miss their moment, and disappear forever. So what if the real evidence was never a message, but something left behind? A machine that doesn't need permission, a structure that leaks heat, a probe that's been waiting longer than humanity has existed. You've heard of SETI listening for radio beacons, but what if the smarter move is to look for the hardware they left behind?
Today we're exploring the shift to SETA, hunting for physical technosignatures, things like industrial heat, engineered pollutants, or long-lived probes that don't need to be on the air to be discovered. We'll show how this changes the odds, why artifacts can outlast signals by millions of years, and where telescopes like JWST could spot excess heat or unusual atmospheric chemistry that biology can't explain. If aliens ever pass through, the traces might still be here. What if the most reliable message isn't a hello in the noise, but a machine that never stopped being there? For decades, the search leaned on radio because radio is cheap, fast, and unmistakably engineered when it's narrowband and repeating. We tuned dishes to quiet parts of the spectrum, hoping for a beacon that cuts through cosmic hiss. That approach assumed a few things: that someone wants to be heard, that they understand our listening habits, that they time their broadcast when our receivers are pointed their way, and that they spend energy to send a clear, artificial signal across light years. It's a tidy framework, cooperative, synchronized, and intentionally directed transmissions. But it hinges on two civilizations agreeing, without ever meeting, on how and when to say hello. Here's where the trap tightens. Radio waves don't vanish, but they spread and thin out. A tight beam misses if our planet isn't in the crosshairs at the right moment. A wide broadcast dilutes into the background. Civilizations might rise and fall on timelines that rarely overlap. So our listening window may open centuries too late or close centuries too early. And beacons aren't free. They take steady power and maintenance, which implies an interest in calling strangers for a very long time. Think about sending a single flare across a dark ocean. It blazes, then fades. If no one looks the instant it burns, the chance is gone. Now think about anchoring a buoy with a light that never turns off. It waits in the same spot, riding the swell day after day. The first approach bets on an instant. The second builds for patience. In cosmic terms, artifacts behave like buoys. They don't need a mutual schedule. They don't rely on a moment of overlap. They persist. That shift leads to a galactic archaeology mindset. Instead of listening for cooperation, you sweep for leftovers, hardware, structures, or power systems that outlive their makers. A dormant probe doesn't care if its creators vanished a million years ago. A passive beacon in a stable orbit can drift for ages. Even the biggest projects leave signatures that don't blend with nature easily. The longer they sit, the more chances we get to catch them. Energy use leaks heat. You can hide a transmitter in a narrow band, but you can't run a vast power network without dumping waste heat somewhere. That's where megastructures come in. A partial Dyson swarm, swarms of collectors in orbit around a star, would reroute energy and glow in the mid-infrared. That excess doesn't need to be perfect or complete. Even scattered collectors and habitats change the star's light in a way that stands out across great distances. Nature produces dust and infrared light too, but engineered systems introduce patterns, temperatures, and stability that aren't easy to confuse when you have the right data. Closer to home, there's the idea of lurkers. If you were going to watch a world quietly, you'd park sensors where gravity helps. Earth-Moon Lagrange points, or co-orbital asteroids that stay near our planet with little fuel. A probe sitting there doesn't have to transmit constantly. It can reflect sunlight oddly, show a non-natural rotation, or carry materials that bounce radar in a way rocks don't. It could nap for eons and still be there when someone finally cares to look. This flips the odds in our favor. Artifact searches don't ask for coordination or goodwill. They ask for durable engineering footprints and the patience to notice them. Instead of minutes of chance during a passing call, you get a geologic scale window. A missed greeting becomes a standing monument that keeps raising its hand. And here's the practical twist. Modern instruments can sniff for the heat and chemistry that industry leaks at scale, signals that biology alone can't fake, while local surveys check the quiet corners of our own backyard. If biology breathes, industry leaks. Could our best clue be waste our tools are built to detect? SETA focuses on technosignatures you can't easily confuse with life alone. 3 stand out. First is mid-infrared waste heat, the thermal glow that any large energy budget has to dump. Second is non-natural atmospheric molecules, the kinds of compounds that don't arise in bulk without manufacturing. Third is geometric fingerprints in light and motion, reflective spectra with sharp edges, regularized orbits, or surfaces that behave more like engineered panels than rock or cloud. Each of these plays to strengths we already have: sensitive infrared eyes, precise spectroscopy, and time series photometry that can spot patterns hidden in noisy data. Biosignatures can fool you. Oxygen can build up from water splitting under strong starlight. Methane seeps from geology. Even haze can mimic complexity. Technosignatures push beyond what nature tends to do at scale. Halocarbons, for instance, don't persist in large amounts without industry feeding them. Nitrogen dioxide can spike from combustion and heavy industrial processes. Sulfur hexafluoride is stable and long-lived, which is handy if you want electrical insulation, but odd if a planet is supposed to be quiet. When you look for multiple markers together, heat plus a suite of pollutants, you start to move from maybe to likely. This is where JWST earns its keep. Its mid-IR instruments read thermal light with precision, which lets you hunt for small temperature bumps that don't match simple climate models. On transiting exoplanets around nearby stars, you can target spectral lines tied to industrial compounds. Chlorofluorocarbon-like molecules absorb in narrow bands. NO2 leaves a recognizable imprint. SF6 stands out in the mid-infrared. You're not guessing. You're tuning to wavelengths where these chemicals cast shadows, then checking if those shadows are deeper than nature tends to dig. Detectability comes down to contrast and time. Around cool, small M dwarfs, a temperate planet blocks a larger fraction of starlight, and its atmosphere imprints stronger features during a transit. That boosts your odds of seeing faint industrial lines, especially if concentrations approach modern Earth levels or slightly above. Some pollutants linger for years to centuries, which means even a civilization that dialed back emissions might leave a detectable afterglow. Others clear quickly, so a detection hints at ongoing activity. Stack many transits, and faint signals can rise above noise. Target the nearest, quietest stars, and the thresholds shift from hypothetical to plausible. Megastructures add a different handle. A partial swarm of power collectors would reroute starlight into work and then heat, producing an infrared excess that doesn't fluctuate like dust clouds and doesn't cool the way debris does after a transient event. Phase curves could look odd, too much warmth on the night side, or a thermal map that suggests heat being shuffled by machines rather than winds. You might see reflectance changes with sharp angles, as if panels rotated, or a temperature plateau that sits at an engineering set point instead of a natural equilibrium. Closer in, SETA turns practical. Survey the Earth-Moon Lagrange points where objects can loiter with minimal fuel. Sweep Earth's co-orbitals and high Earth orbits for surfaces with unusually high or low albedo, radar cross-sections that don't match stone or metal debris, or trajectories that stray from clean Keplerian motion because of active station keeping. Combine optical light curves, radar pings, and thermal data to filter out satellites and junk. What's left, if anything, earns a second pass. The search scales fast when algorithms help. Feed sky surveys from Gaia, TESS, WISE, and LSSD into anomaly detectors that learn natural variability, then flag outliers with engineered-looking regularity or spectra. You're not hand-picking targets. You're sifting millions at once and promoting the weirdest few for deep follow-up. Put together, we already have the reach to probe for industrial heat and chemistry at nearby stars, while our own backyard can be checked for quiet hardware in stable niches. If a single visit ever left a trace, the next clue may sit in a warm infrared bump or a tidy orbit hiding in plain sight, waiting for someone to notice. Signals fade, artifacts persist. SETA stretches the search across centuries and geologic eras, chasing physics that betrays industry, waste heat, engineered chemistry, steady orbits that don't drift by chance. You don't need a handshake. You need a footprint that refuses to disappear. So where would you start? Would you sweep local lurker zones, Earth-Moon Lagrange points, co-orbitals, high orbits, or stare at nearby stars for atmospheres with odd heat and suspicious molecules? The first discovery may not speak. It might glow a little too warm or orbit a little too neatly. A small excess, a tidy curve, and the story tilts toward technology.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.